Hello, I am Edward Berman, and today I'm going to be talking to you about the two numbers and a half problem. As an overview, I'm going to give you the problem statement, talk about the problem difficulty, answer the problem, and give an interpretation on the solution, and then I'm going to prove the algorithm's validity. So the problem statement is the following. Consider the real line. Pick one real number from the line and do not replace it. We're going to pick a second real number. Design an algorithm that guesses whether the second real number is greater or smaller than the first real number with accuracy strictly greater than 50%. All real numbers have an equal probability of being selected. So if you want a better idea of what this means, we may imagine a game where I randomly pick one real number. Uh, the I pick two real numbers, and given that information, some computer will make a guess, and we want this guess to be accurate over 50% of the time. This is a difficult problem to solve because it is impossible to obtain a working solution by picking a random threshold. What I mean by that is you may instinctively think of an algorithm where, okay, if the first get real number that we pick is less than zero, pick greater. If it's greater than zero, pick smaller. But this does not work, and it does not work for any threshold. It doesn't work for zero or e or negative pi or 7, 6 or any real number that you can imagine. So this is the correct answer, or I should say a correct answer. The algorithm is as follows. From a normal distribution 0, 1, sample some threshold t. Pick our first real number x1. If x1 is greater than t, guess smaller, or guess that the second real number is less than x1. Otherwise, guess greater. There's nothing special about a normal distribution here. It just happens to be the simplest case. The idea here is that we're defining a probability distribution over the reals, and that distribution may sample a threshold from three regions. One where the threshold is between the two real numbers, one where it's less than both of them, and one where it is greater than both of them. So let's do a little bit of a more rigorous proof about why this is true. We have A being the event of algorithm success, and we have the three cases, one where T is less than both of the real numbers, one where it's greater, and one where it's in between. If T is less, then we will have an accuracy of 50% because the algorithm will always tell it to pick greater, and that will have a 50% chance of being true. We can say a similar thing for T being above both of them. But if it's in between, then we'll have a 100% chance of winning. Because if our first real number is less than T, then the algorithm will tell us to pick greater, that our second real number is greater than the first one, and this will be true. And the other way around is true as well. If we have our first real number is greater than T, the algorithm will tell T to pick the guess that the next real number is smaller, and this will also be true, sort of by assumption of this case that T sits in between them. So if we use the law of total probability, we can rewrite this expression as follows. This is a half, and this is something greater than a half. If we want to know what this value is, we would have to integrate between these two regions over some density function and find that this is 1/2 plus something. And it doesn't really matter what this is, in fact, because we can choose any distribution over the reals, and the density will still be greater than zero. So then we have found an algorithm that will give us the correct answer over 50% of the time.